An arrow has a velocity vector with components v sub x is equal to 85 meters per second and v sub y is equal to 25 meters per second. What is the arrow's speed and direction with the direction indicated by an angle above the horizontal? So something to note about the way that that angle is described is that is pretty much a description of the standard angle. So if I draw a picture of this vector here, or at least a rough sketch of what I think it might look like, if this is the vector v, it has a fairly large component v sub x. So I think that's that component right there. Here's v sub y, so let me go ahead and label those. This is v sub x again. This is v sub y. And since it says the direction indicated by an angle above the horizontal, that's kind of common language in physics to use that. And I think that corresponds to this angle right there. So again, we're being asked for arrow speed and direction, and that means we're going to calculate what v as the magnitude is, and we're going to calculate what this angle is. Now, I think for magnitude, what we can simply state is that the magnitude v of this vector is equal to the, I like to say sum and quadrature for this. That's a term we're going to use in lab a fair bit as well, is physicists don't just sum, but we sum in quadrature. But basically we're doing the Pythagorean theorem, which is we're adding the two components squared and then square rooting. And this is analogous to the equations on the key concepts page, except there the vector's name was a, and here the vector's name is v, so it changed some of the variables. But how we do it and what we do with it is pretty much the same as always with something like this. So we're going to say, let's see, it was 85. There's units there, so you have kind of a choice here. Like, I think it's cool if you want to just say 85 squared plus 25 squared, and then recognize both those quantities have the same units. They kind of have to do this. You can't do this with two things with different units. And they were squared, and then the whole thing was square rooted. So if you wanted to, you could just kind of put the units at the end here, recognizing that when it's square rooted, the squares of those units would kind of go back to what they originally were. And if you do the algebra, you can see that that was completely legitimate, kind of manipulating the units as if they were variables, and that works out. But at this point, I think I need to go to my calculator and work out what this is as a number. And my calculator says it's 88.6002225, etc. But I think 88.6 for this is going to be a sufficient number of digits to report. So we're going to say 88.6 meters per second. Now, how do we do angle? The thing to remember, maybe I'll write up here really quickly because I'm running a little bit out of space a little bit at the bottom there, is that the tangent of the angle, so let me go ahead and give this angle the name theta. The tangent of that theta should be equal to the ratio of v sub y to v sub x, and that makes sense based on the right triangle. It's also kind of like one of the formulas that we saw on the key concepts page. That maybe you could write in some notes somewhere if you think you're going to forget it. But in this case, I think it's going to work out. This angle is going to be some small angle. I think it'll work out to just write that angle is going to be equal to the tangent inverse. In other words, one of the maneuvers that you can do with any trigonometric equation where you're trying to solve for what's inside is you take the inverse trig function of both sides, and that basically undoes it on the side, on the left side here. But then on the other side, you'd have tangent inverse of vy over vx, which maybe I'll put some parentheses there. In this case, that means I'm going to go to my calculator and put in tangent inverse of 25 divided by 85. And I don't need to worry about units here because they cancel out top and bottom, so I don't need to bother to write them for a thing like this when they cancel. I've gone ahead and put that in my calculator, and I'm getting like 16.38954. I think, I often get a little uncomfortable using sig fig rules with angles, I've said, but not really knowing much else. I think we're probably the best course of action to take here if we want to kind of do justice to uncertainty and how that is represented by significant digits. Rounding off to 3 significant digits seems like the appropriate choice. Really, if this were something where we knew a measurement error, we'd have to do a more complicated kind of propagation of uncertainty, which actually for trig functions involves a bit of calculus, so we usually don't do that in our class. Maybe the one thing I could add down here, though, is to say this is a degree measure, 16.4 degrees. So a question that sometimes comes up as well in this class is, do I need to convert this into radians? And my answer is no, you don't have to, but it's good to use correct notation, and in that sense, both these answers include units. And for the angle, if it's in degrees, that includes the degree mark, even though it's not really a physical unit, but still it should be included.